What if, right now, something out there is watching us? Not through radio waves or blinking lights, but through presence. In the black stillness beyond Neptune, a small traveler crosses the void, faster than any comet, stranger than any asteroid. It doesn't spiral. It glides, steady, deliberate, silent. Astronomers named it 3-Eye Atlas, the third visitor ever confirmed from another star. But from the moment it appeared, one question began to ripple across every observatory on Earth. What exactly have we just met? Its path bent where physics said it shouldn't. It moved as if powered by something unseen. And when sunlight struck its surface, it shimmered, not like ice, but like intention. Some said coincidence. Others, something else. Harvard astrophysicist Avi Loeb called it a mothership, a relic of minds older than our sun, passing quietly through our solar system. Across the world, scientists turned their eyes and antennas toward the sky, searching for proof, or perhaps permission to wonder again. Because sometimes, discovery isn't about what we see, it's about realizing the universe might already be looking back. So tonight, beneath this same sky, ask yourself, if the first message from another civilization isn't a signal but a visitor, what happens next? Tell us in the comments. Which country are you watching from? Subscribe to Whisper Science, where the universe speaks in quiet tones and humanity learns to listen. In the silent vastness beyond Pluto's orbit, in the dim reaches where the sun's warmth barely stirs, a faint wanderer arrived. On July 1st, 2025, the Sky Survey instrument known as Asteroid Terrestrial Impact Last Alert System, ATLAS, scanning the heavens from its station in Chile, recorded a moving point of light. It flickered amid the stars, unremarked at first, but careful analysis revealed that this was no ordinary body bound to our sun. It was later designated 3-Eye Atlas, the third confirmed interstellar object ever observed in our solar system. From that moment, the trajectory was unmistakable, a hyperbolic path, a speed at infinity, v infinity, far exceeding what any mere solar system object would carry. The initial orbital solution indicated an incoming speed approaching 58 km/s, meaning this traveler had not formed in our sun's family. It came from the star's astronomers knew two prior interstellar interlopers. The first, 1-Eye Oumuamua, detected in October 2017, and the second, 2-Eye Borisov, in August 2019. Each challenged notions of what might drift into the solar system from afar. But 3-Eye Atlas arrived in an era of far greater observational readiness. We had wider field surveys, faster detectors, and telescopes ready to pivot. Its detection was therefore less a miracle of luck and more a testament to our sharpened gaze. Once discovery alerts circulated, telescopes around the globe pivoted. Observatories in Hawaii, Chile, and elsewhere gathered stacks of images. The faint glow of 3-Eye Atlas revealed subtle aspects. First, a compact coma, a halo of gas or dust enveloping the nucleus. In the deep imaging by the Canada-France-Hawaii telescope and the Very Large Telescope, a small fuzz of material seemed to surround the object at spectral slope in visible and near-infrared wavelengths measured around. 17.1 plus or minus 0.2% per 100 nanometers, a value comparable to some D-type asteroids and primitive comets, and yet, despite these commonalities, the details diverged. The incoming radiant of 3-Eye Atlas was traced to a region near the galactic center direction, making early detection challenging due to the dense star field and high background on the matter of size. Initial brightness estimates, assuming typical albedo, would place the nucleus at perhaps 20 kilometers diameter if it were an asteroid. Yet if it were comet-like and dominated by a coma's brightness, the solid core might be significantly smaller. The discovery papers flagged this uncertainty. Why did 3I Atlas come now? This question echoed through the corridors of observatories and journal preprints. Part of the answer lies in coincidence. Humanity's survey instruments have matured to the point where interstellar wanderers no longer slip by unseen. When Oumuamua arrived in 2017, our all-sky monitoring was less sensitive. When Borisov arrived in 2019, systems had improved, but 3I Atlas benefited from yet another leap. The improved cadence and sensitivity of Atlas, the Pan-STARRS network, ZTF, and follow-up spectroscopy meant that a visitor from outside could be not only discovered but characterized. This juxtaposition, rare object, improved instrumentation, allowed the object's origin and properties to be probed in unprecedented detail to understand the rarity of this event. One must reflect on what interstellar object means. Most small bodies seen in the solar system, asteroids, comets, abound. Their orbits remain elliptical, looping around the Sun. But interstellar objects arrive on trajectories that do not close. They carry enough energy to escape the Sun's gravity, indicating a far distant genesis. Prior to discoveries in the 21st century, they were purely theoretical. But with Oumuamua, Borisov, and now 3I Atlas, they have become real, tangible messengers. The importance lies not only in their extrastellar origin, but in the story they carry. They are fragments of other star systems, bearing chemical, dynamical, and structural clues of formation beyond our Sunday. 3I Atlas raised immediate interest because its dynamical and physical parameters suggested something more than a simple cosmic rock. In particular, the light curve variations were surprisingly minimal over a 4-day observation interval, which could hint at a relatively spheroidal shape or perhaps an object whose rotation and orientation minimize brightness fluctuations. The object's inbound path lay only ~5 degrees from the ecliptic plane, an unusually low inclination for an interstellar visitor. Adding to the mystery, AS telescopes around the world monitored it. A subtle but growing sense of anticipation filled the scientific community. What if this object offered a window into processes far older than our solar system? What if the sampling of material from another star system, now passing through our celestial neighborhood, could tell us how planetary systems form, migrate, and evolve across the Milky Way? This sense of wonder blended with caution. The idea that we would capture such a visitor was thrilling, but interpreting the data demanded rigor. One misstep, one overclaim, and the community would recoil. Into this context entered the voice of Avi Loeb, astrophysicist at Harvard, known for pushing boundaries. Loeb emphasized that the first contact humanity might have with another civilization need not arrive as a radio signal. It might come as an object passing through our system, silent yet observational. He urged that the community keep an open mind, even while adhering to stringent scientific discipline. His early commentary, while provocative, served to widen the scope of inquiry rather than shrink it, and so the stage was set. A rare visitor, detected by the sharpened eye of modern telescopes. Data streaming back from multiple observatories. Hints of unusual behavior, combined with a global scientific community poised between awe and skepticism. The story of 3I Atlas had begun, not merely as a passing curiosity, but as a mystery spanning stars, time, and possibility. In the silent vastness beyond Pluto's orbit, in the dim reaches where the sun's warmth barely stirs, a faint wanderer arrived. On July 1st, 2025, the sky survey instrument known as Asteroid Terrestrial Impact Last Alert System, ATLAS, scanning the heavens from its station in Chile, recorded a moving point of light. It flickered amid the stars, unremarked at first, but careful analysis revealed that this was no ordinary body bound to our sun. It was later designated 3I Atlas, the third confirmed interstellar object ever observed in our solar system from. That moment, the trajectory was unmistakable, a hyperbolic path, a speed at infinity, v infinity, far exceeding what any mere solar system object would carry. The initial orbital solution indicated an incoming speed approaching tilde 58 km rs, meaning this traveler had not formed in our Sun's family. It came from the stars astronomers knew two prior interstellar interlopers. The first, 1I Oumuamua, detected in October 2017, and the second, 2I Borisov, in August 2019. Each challenged notions of what might drift into the solar system from afar. But 3I Atlas arrived in an era of far greater observational readiness. We had wider field surveys, faster detectors, and telescopes ready to pivot. Its detection was, therefore, less a miracle of luck and more a testament to our sharpened gaze. Once discovery alerts circulated, telescopes around the globe pivoted. Observatories in Hawaii, Chile, and elsewhere gathered stacks of images. The faint glow of 3I Atlas revealed subtle aspects. First, a compact coma, a halo of gas or dust enveloping the nucleus. In the deep imaging by the Canada-France-Hawaii telescope and the Very Large Telescope, a small fuzz of material seemed to surround the object at spectral slope in visible and near-infrared wavelengths measured around 17.1 plus or minus 0.2% per 100 nanometers, a value comparable to some D-type asteroids and primitive comets. And yet, despite these commonalities, the details diverged. The incoming radiant of 3I Atlas was traced to a region near the galactic center direction, making early detection challenging due to the dense star field and high background on the matter. Of size, initial brightness estimates, assuming typical albedo, would place the nucleus at perhaps 20 kilometers diameter if it were an asteroid. Yet if it were comet-like and dominated by a coma's brightness, the solid core might be significantly smaller. The discovery papers flagged this uncertainty. Why did 3I Atlas come now? This question echoed through the corridors of observatories and journal preprints. Part of the answer lies in coincidence. Humanity's survey instruments have matured to the point where interstellar wanderers no longer slip by unseen. When Oumuamua arrived in 2017, our all-sky monitoring was less sensitive. When Borisov arrived in 2019, systems had improved, but 3I Atlas benefited from yet another leap. The improved cadence and sensitivity of Atlas, the Pan-STARRS network, ZTF, and follow-up spectroscopy meant that a visitor from outside could be not only discovered but characterized. This juxtaposition, rare object, improved instrumentation, allowed the object's origin and properties to be probed in unprecedented detail. To understand the rarity of this event, one must reflect on what interstellar object means. Most small bodies seen in the solar system, asteroids, comets, abound. Their orbits remain elliptical, looping around the Sun. But interstellar objects arrive on trajectories that do not close. They carry enough energy to escape the Sun's gravity, indicating a far distant genesis. Prior to discoveries in the 21st century, they were purely theoretical. But with Oumuamua, Borisov, and now 3I Atlas, they have become real, tangible messengers. The importance lies not only in their extrastellar origin, but in the story they carry. They are fragments of other star systems, bearing chemical, dynamical, and structural clues of formation beyond our Sun. 3I Atlas raised immediate interest because its dynamical and physical parameters suggested something more than a simple cosmic rock. In particular, the light curve variations were surprisingly minimal over a 4-day observation interval, which could hint at a relatively spheroidal shape or perhaps an object whose rotation and orientation minimize brightness fluctuations. The object's inbound path lay only tilde 5 degrees from the ecliptic plane, an unusually low inclination for an interstellar visitor, adding to the mystery. As telescopes around the world monitored it, a subtle but growing sense of anticipation filled the scientific community. What if this object offered a window into processes far older than our solar system? What if the sampling of material from another star system, now passing through our celestial neighborhood, could tell us how planetary systems form, migrate, and evolve across the Milky Way? This sense of wonder blended with caution. The idea that we would capture such a visitor was thrilling, but interpreting the data demanded rigor. One misstep, one overclaim, and the community would recoil. Into this context entered the voice of Avi Loeb, astrophysicist at Harvard, known for pushing boundaries. Loeb emphasized that the first contact humanity might have with another civilization need not arrive as a radio signal. It might come as an object passing through our system, silent yet observational. He urged that the community keep an open mind, even while adhering to stringent scientific discipline. His early commentary, while provocative, served to widen the scope of inquiry rather than shrink it, and so the stage was set, a rare visitor, detected by the sharpened eye of modern telescopes, data streaming back from multiple observatories. Hints of unusual behavior, combined with a global scientific community poised between awe and skepticism. The story of 3i Atlas had begun, not merely as a passing curiosity, but as a mystery spanning stars, time, and possibility. In the weeks and months following the discovery of 3i Atlas, the third known interstellar visitor to cross our solar system, a quiet but profound phenomenon began to emerge. Astronomers charted its path with increasing precision, expecting to see a trajectory governed solely by gravity and the sun's familiar pull. Instead, they found something altogether more unsettling. The visitor was moving in slight ways that gravity alone could not fully explain. From the earliest orbital solutions, 3i Atlas presented an incoming hyperbolic excess velocity toward the Sun of approximately 58 km/s. Its eccentricity of roughly e almost equal to 6.1 and perihelion around 1.36 AU implied an origin beyond our solar system, an interstellar wanderer. But more than that, the orientation of its orbit, an inclination near 175 degrees, retrograde relative to the ecliptic, and a trajectory that skimmed into the inner system triggered immediate questions. As observations accumulated, teams turned their attention to subtle deviations from the gravity-only model. Tiny residuals in the astrometric positions of 3i Atlas, when compared to the best-fit gravitational orbit, suggested either unmodeled forces or unexpected behavior. A leading study found that the upper limit on any non-gravitational acceleration was about 3 times 10 to the power of 1 AUD squared, an astonishingly small number, but significant in the context of our best measurement precision in ordinary comets within the solar system. Non-gravitational acceleration arises from jets of sublimating ice. As the sun warms the surface, gas escapes and acts as tiny thrusters, altering the path. But 3i Atlas offered none of the familiar signatures in full. No clearly defined coma radial expansion that matched expected outgassing models. No tail geometry entirely consistent with those models. In other words, the normal physical mechanisms strained to fit the data. Polarimetric observations deepened the shock. 3i Atlas exhibited an unusually strong negative polarization branch, reaching Oumuamua phase angles near 7 degrees, and an inversion angle unexpectedly low at tilde 17 degree. According to Gray et al., this combination is unprecedented among both asteroids and comets, including the earlier interstellar object 2I Borisov. These optical fingerprints hinted at surface or dust grain properties outside the typical suite of icy solar system visitors, suggesting a different composition, a different internal structure, perhaps even a different origin story, then came. The bombshell, a provocative paper by Loeb, Crowell and Loeb, raised the possibility that an astronomical object behaving this way might warrant thinking beyond natural bodies alone. That is, they proposed, even if tentatively, that 3I Atlas might be a technological object, or at least one whose behavior defies comfortable classification. The mere mention of such a hypothesis sent ripples through the community. It was a scientific shock, not because the idea itself was accepted widely, but because the data forced the discussion into one of the most delicate regions of science: what counts as natural, what counts as engineered, and how carefully one must discern between them. The shock deepened when composition-related observations emerged. A team reported detection of hydroxyl gas, signature of water, being released from 3I Atlas at a heliocentric distance of about 2.90 AU, where solar heating is weak. The release was estimated at some 40 kilograms s to the power of 1. That rate of water release so far from the Sun challenged the canonical picture of cometary activation, where volatiles begin to sublimate at much closer distances. The anomaly was layered: unusual orbit, odd polarization, marginal non-gravitational acceleration, and now outgassing at unexpected distance. On August 10, 2025, the Hubble Space Telescope captured high-resolution images of 3I Atlas, which clarified its morphology but also emphasized its unusual features: no obvious, long, sweeping tail, a diffuse coma, brightness variations not fully consistent with standard models. The more the visitor was examined, the less it seemed to fit the standard comet mold. Scientists accustomed to classifying objects into the neat categories of asteroid versus comet found themselves unsettled by the persistent outlier. This tension between clean models and messy reality is where the scientific shock truly lies. Because in science, anomalies matter. They are the cracks in the pavement that may lead to new ground. For decades, our understanding of small bodies in the solar system rested on frameworks established by pioneers like Clyde Tombaugh, Eugene Shoemaker, and even drawing on early work by Kip Thorne and Stephen Hawking, who emphasized the role of fundamental forces and symmetries. To face an object traveling through the solar system that refuses those regularities is to stand, in essence, at the edge of expectation. Moreover, the object's encounter rate, its near-ecliptic inclination, and the tight alignment of its orbital plane with that of the planets added to the unease. In the Loeb analysis, the probability of the observed alignments of 3I Atlas approaching Venus, Mars, and Jupiter with particular closeness was estimated at less than 0.005%. Such low probabilities suggest either a rare natural fluke or something guided by processes not yet known within the scientific community. The reaction was measured, yet intense. Some researchers urged caution. There are many flavors of comets, and we have only glimpsed 2 interstellar objects before this one. Others whispered that the anomaly might be the whisper of something truly profound. Among the astrophysicists, the phrase non-gravitational acceleration began to flicker not only as a measurement error possibility, but as an indicator of hidden forces. It is worth emphasizing that the most recent rigorous study, Chloe et al., constrained the non-gravitational acceleration to be very small, which complicates any theory of active propulsion or dramatic jetting. That finding does not eliminate anomalies, it sharpens them. If there is little non-gravitational thrust, yet compositional and orbital behaviors are odd, then the searchlight shifts. Maybe the composition, shape, or internal structure are atypical in ways that produce subtle but distinct effects. As this chapter draws to a close, the sense of scientific shock is not about panic or extraterrestrial sensationalism, but about being confronted with the unknown in a way that demands humility. Here is an object from deep space that slides through our solar system, disturbed only slightly by gravity, yet rendered intensely interesting by its divergence from expectation. And in that divergence lies not just curiosity, but the possibility of expansion of our cosmic narrative. The stage is set for deeper investigation, for probing the mechanisms, the materials, the trajectory refinements, and for shifting from what is it to what does it imply. The shock may be the beginning of a new chapter in observational science, a chapter where interstellar objects become more than passing curiosities, and instead serve as messengers of what lies beyond our familiar horizons. The moment when an object from afar drifts into our solar system is an invitation. It invites sight, measurement, speculation. For 3I Atlas, that invitation was answered by a global network of telescopes, each trying to read its still flickering message across the void. As the object moved through the inner system, the deeper investigation began, tracing not only its orbit but its nature, composition, dynamics, and the hints of what it might mean. In the earliest hours after its discovery on July 1st, 2025, astronomers worked to pull out every photon, every pixel from the surveys that first flagged it. Then came the backward search, the pre-discovery frames. The Transiting Exoplanet Survey Satellite, TESS, data were combed between May 7th and June 2nd, 2025, revealing that 3I Atlas had been quietly drifting through TESS's field of view long before we realized it. Those faint, unsuspecting recordings became a time capsule of the object's inbound journey. That earlier immersion meant its motion across the sky, its light curve behavior, and its brightness evolution could be constrained in ways seldom possible for comets or asteroids in the solar system. As the object drew closer, the larger telescopes volunteered. The Vera C. Rubin Observatory, still in commissioning, recorded images from June 21st onward, detecting the faint glare of 3I Atlas and even signs of activity. These glimpses revealed a diffuse coma surrounding the nucleus. Stars and background galaxies showed up, and then the visitor's fuzzy halo glowed faintly, like a ghost in the night. It was a moment of quiet astonishment, not just that this object had arrived, but that we had the tools to study it with such fidelity. From these observations emerged the first physical parameters. The orbit was hyperbolic, eccentricity approximately 6.1, perihelion at around 1.36 AU, an incoming velocity at infinity of roughly 58 kilometers per second. The inclination was nearly 175 degrees, a nearly retrograde path relative to the ecliptic. These numbers alone told a story. This is not a body formed in our solar system, but one that traveled from afar, swept by interstellar space, now passing through our neighborhood. But motion is only one part of the puzzle. Composition matters. Spectroscopic data arrived, showing that 3I Atlas bore telltale signs of activity. Ultraviolet imaging from July 31st to August 1st revealed emission from hydroxyl, OH, the breakdown product of water, indicating that the object was releasing water vapor at a heliocentric distance of about 3.51 AU, a zone where solar heating is normally too weak for classical sublimation to dominate. That finding alone raised the question, how does water escape so far from the sun's warmth? For a comet forming in the solar system, that behavior is unusual. For an interstellar object, it suggests a fresh set of rules. Measurements of the Co-HO ratio, obtained with the James Webb Space Telescope, JWST, offered an even stronger hint of difference. At an inbound heliocentric distance of 3.32 AU, the infrared spectra revealed a co-dominated coma with a Co-HO mixing ratio of about 8:1, among the highest ever measured for any comet. The implication: Either the nucleus of 3I Atlas is enriched in co-ice compared to water ice, or its thermal structure suppresses water sublimation relative to co. Perhaps it formed in an environment radically different from our own, or spent eons in deep interstellar cold, preserving volatile reservoirs that solar system comets lost. Light curve studies added further intrigue. The brightness variation over 4 days immediately after discovery was minimal, which contrasts strongly with many solar system comets, where rotation of the nucleus or asymmetric activity produces fluctuations. In one dataset from early July, 2 moderate brightenings appeared, but detailed analysis suggested they were artifacts of seeing conditions and contaminating stars. The absence of a clear rotational signature suggests either a highly symmetric body, an orientation such that rotation signatures are hidden, or a nucleus enshrouded in coma whose kinetics swamp the rotational modulation. Polarimetric observations deepen the mystery. In September 2025, measurements taken with FIRS-2 at the Very Large Telescope, ALPHOSC at NOT and other instruments showed that 3I Atlas exhibited a deep and narrow negative polarization branch, reaching about -2.7% at phase angle near 7 degrees and an inversion angle of -17 degree. That combination is unprecedented among comets and asteroids in the solar system. What could this tell us? Possibly a surface composed of unusual materials, or dust particles shaped or structured differently, or perhaps an evolutionary history unlike any solar system visitor. Alongside these data, the object's dynamical context grew more concrete. A study examining its kinematics and possible origin suggested the object may hail from the galaxy's thick disk, a region of older stars, low in heavy elements, dating back perhaps 9 to 13 billion years. If so, 3I Atlas may be a relic of ancient times, giving scientists a glimpse not only of another star system but of a long-gone epoch of the Milky Way's formative history. Each thread of investigation, the orbit, the coma chemistry, the light curve, the polarization, added depth. Instead of a simple comet, 3I Atlas began to look like a messenger with multiple secrets, of origin, of formation, of structure. To interpret these clues, scientists expanded their toolkit: thermal models, dust grain scattering theories, dynamical ejection simulations, and comparative analyses with known solar system comets like C2016R2, the unusually Courage comet, and classic long-period comets. One question arose early. If the nucleus is active at 3.5 AU and releasing water at ~40 kg(s⁻⁴), based on OH emission, then the active surface area must be unusually large, perhaps over 20% of the surface face sublimating. For a typical solar system nucleus, that would be atypical. For an interstellar body, it suggests a less thermally processed, more pristine object. Meanwhile, the high co-HO and lack of strong light curve modulation hint at a different internal structure, maybe large icy grains, maybe a fluffier aggregate, or perhaps weak cohesion where dust and ice interplay differently. Another crucial layer was the trajectory. The nearly ecliptic aligned, low inclination retrograde orbit, near the plane of the planets, proved puzzling. Most interstellar objects expected to arrive randomly, yet this one entered in a path almost aligned with our system's plane. Some models flagged this alignment as highly unlikely under random arrival hypotheses, prompting questions whether there might be biases in detection or unknown processes directing such objects into inner solar system trajectories. And the world of telescopes. Each new observation tuned the narrative. At the Canada-France-Hawaii Telescope and the Very Large Telescope, observers captured deep stacks that resolved the coma and searched for a tail. The results: A faint tail was present, but not as long or dramatic as many solar system comets at similar distances. The dust coma appeared diffuse, and in high-resolution imaging, the surface brightness profile suggested a coma that extends tens of thousands of kilometers, yet no large jets were resolved. Thermal modeling again suggested an insulating dust mantle, possibly preserving interior volatiles while allowing limited activity. Interpretation of all these clues required humility. Scientists noted that even within the solar system cometary population there is diversity, so an interstellar visitor could reasonably show new behaviors without requiring exotic provenance. Yet when multiple metrics point to oddity, chemistry, polarization, orbit alignment, the need for alternate hypotheses becomes stronger. The investigation moved from asking, "What is this?" to "What does this tell us?" The narrative of 3I Atlas thus shifted. It was no longer simply a cosmic visitor. It became a bridge between star systems, between epochs, between what we thought we knew and what remains open. The body's story is inscribed in its motion and in the subtle glow of its coma. It speaks of ejection from a parent star, a long wandering across galactic space, a plunge into the sun's domain, and now a slow departure back into obscurity. The investigations are tracing its lines: the volatile inventory, the dust grain structure, the surface composition, the dynamical history. Each offers a clue to how other planetary systems evolve and what material journeys through the galaxy. And so the deeper investigation continues. Teams prepare for future imaging, spectroscopy, polarization runs. Dusty tails will be modeled, active areas estimated, grain size distributions inferred. Each dataset adds a layer of context. In months and years to come, the archive of 3I Atlas will stand among the most studied interstellar objects. It will be compared not just against solar system comets, but against exoplanetary debris and theoretical models of planetesimal ejection and interstellar transport. Through all this, one truth emerges: to see 3I Atlas is to see a fragment of another world, another time. And in tracing its passage, the scientific community may learn not simply about this object, but about what other star systems throw into the galaxy, and how our own solar system may one day do the same, die in the dim light of its coma and on the path of its hyperbolic flight. The visitor carries questions that deserve more than mechanics. They deserve reflection on our place in a dynamic, interconnected cosmos. A visitor from the stars had already unsettled the comfortable categories of asteroid and comet. Yet for the object designated 3I Atlas, what arrived next was a gathering of puzzles that did not peel away into clarity, but deepened into enigma. In the weeks after its identification, the data did not settle. They rippled outward. The mystery escalated. At first glance, the orbit had seemed exceptional but comprehensible. A hyperbolic trajectory, high incoming velocity, a path from outside our solar system. But then questions multiplied. Why was the object's inclination and orbital plane so closely aligned with the ecliptic, when most random arrivals from interstellar space should cross at any angle? Why did the object appear faintly active at large distances from the Sun, when solar heating should be insufficient? Why did the polarization measurements fall outside known ranges? Each answer seemed to open deeper questions. In late August 2025, images from the Hubble Space Telescope and ground-based giant telescopes revealed the growing extent of the coma surrounding 3I Atlas. What had been a subtle fuzzy halo now spread tens of thousands of kilometers around the nucleus. Yet the tail, when present, was weak, broad, and lacked the crisp streaming of dust seen in many solar system comets. It was the first indication that the physical mechanisms at work might differ in kind, not just in degree. The tail shape and direction revealed a weak anti-solar component, suggesting the action of solar radiation pressure and sublimated dust. But the relative weakness of that tail pointed to either a low dust-to-gas ratio or a dust population very different from expectations, concurrently. The polarimetric behavior of 3I Atlas delivered a startling result. Measurements taken at phase angles between -8° and -22° showed a negative polarization branch reaching about -2.7% at -7°, with an inversion angle of -17°, features not seen in solar system comets or asteroids. That suggests the surface or coma particles of 3I Atlas have textures, sizes, or compositions outside the norm. Some of the observed values match those seen in certain trans-Neptunian objects or centaurs, hinting at an origin in the deep frigid reaches of a star system, or possibly a long residence in interstellar cold. Whatever the source, the result emphatically broke rank with known comet behavior as September unfolded. Production of water, inferred via OH emission, was detected at a heliocentric distance of -3.5 AU, a cold region for conventional sublimation. The implied water production rate, roughly 40 kilograms s to the power of 1, required that a large fraction, over 20%, of the surface area be actively outgassing if the nuclear size is modest. That level of activity so far from the Sun is rare even among solar system comets. The Co-HO ratio measured by the JWST was about 8 plus or -1, placing it among the most co-rich comets ever seen. Together, these pieces contributed to a new, an easy conclusion. 3I Atlas might not simply be a regular comet from another star, but one that formed in an environment radically different, beyond the physical properties. The geometry of the encounter added to the tension. The orbit of 3I Atlas carries it past Mars, then within near-Saturn orbits, then out again, but the approach vector lies only about 5 degrees from the ecliptic. Many models of interstellar object arrival predicted a more isotropic distribution, yet here was a case aligned with our planetary plane. Some analysts estimated the probability of such alignment at under 0.5% if arrivals were random, raising faint alarms. Could something be biasing the entry? Observational selection effects were discussed, southern sky surveys, dense star fields, yet even after correction, the alignment remained curious. At this juncture, the tone within astronomy subtly shifted. What had been interesting interstellar visitor morphed into object of serious anomaly. Yet the community held its discipline. Data, not speculation, must lead. The tensions between Seth's remark that anomalies are the fuel of discovery and the preparedness not to mistake noise for signal became acute. Some researchers emphasize that the known sample of interstellar objects is vanishingly small, 2 prior examples only, so diversity should be expected. Others pointed out that multiple anomalous parameters across independent instruments collectively hint at something more than random variation. As the narrative escalated, media interest followed. Headlines suggested alien probe, cosmic messenger, even warning. Within the corridors of universities and observatories, scientists bristled at overinterpretation, but the underlying emotional undercurrent of being confronted by truly novel phenomena was undeniable. The sense that something had arrived which tested our classification, our models, our expectations. In the laboratories and computing clusters, teams modeled the thermal evolution of 3I Atlas. If the co-abundance is so high, then maybe the body formed near the co-ice line in its parent disk, or perhaps in an environment where water-ice sublimation had over time depleted the surface layers, leaving co-ice still intact. Simulations of cosmic ray exposure over billions of years indicated that interstellar transit could have eroded volatile mantles, but then the sheet of 3I Atlas seemed too active. Some modeled a dust mantle thick enough to inhibit water sublimation, yet still allow bursts of activity when heating penetrated that mantle. Others suggested the possibility of crust cracking triggered by perihelion passage, releasing internal volatiles in a threshold response. That scenario could explain the late onset of activity and the minimal tail. Yet even these models left pieces unaccounted. The weak tail, the minimal rotational brightness variation, the alignment of incoming path, the polarimetric oddity, all pointed away from standard comet paradigms and toward the possibility of an unusual internal structure or even an unusual origin. Among theorists, the whisper began, if nature produces such variety, perhaps there are object types as yet uncatalogued, planetesimal relics, ultravolatile bodies, or even engineered craft launched by extraterrestrial intelligence. The last idea remained fringe in the professional literature, but the tension was real. Amid all this, the scientific instruments themselves became part of the story. Observatories in Chile, Hawaii, Arizona, the Canary Islands all lined up beams of light and spectrographs at 3I Atlas. They trained ultraviolet sensors. They reviewed archival data. They scanned for outbursts. They polled historical surveys. The volume of data multiplied. Rather than converging toward an explanation that neatly fit, the data spread outward, like ripples expanding across a pond whose center had been disturbed. Each new piece of information added not resolution but further depth. Complexity. As October approached, the expectation was that perihelion, its closest approach to the Sun, would offer heightened activity and critical insights. Might it fragment? Might jets appear? Might its brightness spike? Observers prepared for the display. The possibility of a surprise, unexpected fragmentation, or sudden activity hung in the air. The mystery was no longer simply academic. It had texture, urgency. For the scientific community, the escalation of the mystery forced a reckoning of sorts. The solar system is no longer a closed domain of familiar small bodies. Visitors from the galaxy carry unfamiliar signatures. Our models of icy bodies, dust ejection, tail formation, nuclear rotation, polarization, volatile reservoirs, each must be examined again in light of what 3I Atlas presents. The recognition grew that interstellar objects might not arrive as neat analogues of solar system comets. They might bring surprises by design of their origin, environment, history, or unknown influences, and beneath the science, quietly, lay existential weight, the notion that something from afar had entered our system and refused to behave as expected. That our instruments caught it is a triumph. That it now resists straightforward classification is a challenge. The escalation of its mystery is not failure, but opportunity. To peer deeper, to question assumptions, to expand our taxonomy of cosmic visitors. In that moment, as the world prepared to watch a comet, or something like one, approach its closest solar passage, the scientific community collectively held its breath. The visitor named 3I Atlas had arrived. The data were in. And instead of yielding tidy answers, the object had offered more questions. The stage was set for theories to surge, for observations to intensify, for history to acknowledge that the next frontier might lie not in distant exoplanets, but in the small wanderers that cross our path. The visitor known as 3I Atlas continues to drift outward, but in its wake travels a wave of questions far more than answers. In this chapter, the narrative shifts, not from measurement to mystery, but from mystery to possibility. Here, the data invite not only interpretation, but bold speculation. The standard classification strained, the object opens a door into alternative cosmic narratives. each anchored in science, yet reaching toward what we do not yet know. One line of theory begins with civilization-scale engineering, drawing on the trajectory, alignment, and anomalous parameters of 3I Atlas. Some scientists ask whether the object could be technological, a probe, a relic, or even a sentry dispatched by an extraterrestrial intelligence. That hypothesis lifts from astrophysical curiosity into profound implication. The object's incoming path lies nearly in the ecliptic plane, a geometry that, under random arrival assumptions, has a low probability. Its polarimetric fingerprint, its high co-outgassing relative to water, its minimal rotational modulation, all combine into a pattern that some argue is more plausible for an engineered craft than a typical icy comet. In this scenario, 3I Atlas is not simply bait returning from the stars, but part of an interstellar surveillance network, a silent warning or first contact through presence rather than signal. Yet this theory collides with scientific caution. Extraordinary claims must rest on extraordinary evidence. No unambiguous technological signature, thrusters, structural symmetry, active navigation has been observed. The community reminds us that exotic natural formations can mimic engineering. The speculative hypothesis does not presuppose alien intent. Instead, it treats the possibility seriously, as a scientific test rather than a headline. Under this framing, 3I Atlas becomes a catalyst for expanding what constitutes an object in our celestial neighborhood, not only fragments of stars, but artifacts of minds we have yet to meet. Another branch of speculation turns inward to cosmic evolution, the relic hypothesis. What if 3I Atlas is not a probe, but a fragment from an ancient civilization, its launch long since decayed, its engine cold, its journey unremarkable until now? In that view, the high Co-HO ratio might reflect ejection from a low metallicity system, its retention of volatile ices preserved over billions of years. The minimal rotational variation suggests either a near-spherical structure or a body encrusted in a dust mantle that mutes changes, a body quietly drifting, perhaps intentionally or perhaps not, through interstellar space. It becomes the doll in the cosmic attic, an object that outlived its makers, carrying the chemical fingerprint of worlds older than our own. This leads to a third speculative axis, the galactic ecological hypothesis. If interstellar objects like 3I Atlas are numerous, and many models now suggest thousands cross the solar system per million years, then perhaps they are the seeds of planetary systems, the scattershot of planetesimals ejected by growing stars, gravitational encounters, or explosive events. 3I Atlas could be one such seed, enriched in CO and expelled into the galaxy early in its system's history. From this vantage point, the object is natural, but its discovery invites a new view of cosmic ecology. Planetary systems do not end neatly but cough up debris into the galaxy, transport it across millions or billions of years, and perhaps return it to other systems like ours. In this light, the object is not a singular anomaly but a chapter in a grand cosmic circulation. Each of these speculative frameworks invites deep questions. If it is technological, how many such probes traverse the galaxy unnoticed? If it is a relic, what civilization launched it? If it is part of an interstellar ecosystem, how common are such travelers and how much do they revise our picture of planetary system evolution? These are not idle philosophical curiosities. They suggest experiments, observations, and theoretical work that push science into uncharted territory. Embedded in all these possibilities is the heritage of Einstein and Hawking, integrity of measurement, humility before the unknown, the invitation to probe where the phenomena lie at the edge of known physics. Einstein's relativity told us that mass and energy curve spacetime. Hawking taught that even black holes can leak information. In that spirit, An interstellar object that resists classification may be telling us something deeper about cosmic transport, memory, and the legacy of stars. We must resist the temptation to settle quickly into one interpretation. If 3I Atlas is simply an exotic comet, that itself is momentous. If it is artificial, that is transformative. The path ahead is lined with data yet to arrive, but the speculations are already stirring. Over the next years, astronomers will watch for additional objects, refine detection methods, and broaden surveys. But for now, humanity sits with a guest from beyond, and the guest offers not only data but questions about origin, purpose, design, and the nature of cosmic solitude. The poetic core returns. Perhaps 3I Atlas carries a message, not in explicit words, but simply by being here. If it was engineered, the message may be you are not alone. If it is natural, the message may be the galaxy is full of wanderers. If it is relic, the message may be civilizations rise and fall, and their echoes drift on for eons. All three converge on the same essential truth: the universe is not static. Our solar system is not hermetically sealed. In this moment of speculation, the object stands as both mirror and horizon. It reflects our capacity to wonder and points toward what we may yet understand. And so the scientific community holds the speculative space wide open. Models will be built, surveys expanded, instruments trained. Theories will compete: natural versus engineered, relic versus seed, random versus directed. None yet wins, because the data still accumulate. But the act of speculation, the courage to ask what if in measured fashion, is itself part of the story. In the end, the visitor we call 3I Atlas has done more than pass through our system. It has recalibrated our questions. It has asked us to consider not only what the object is, but how we see ourselves. Are we the first? Are we rare? Or are we part of a crowded cosmic workshop where messages may come not in words, but in motions, materials, and alignments? The theories and speculations swirl, and the next chapters of observation await. Night after night, the instruments stand ready: telescopes, spectrographs, polarimeters, and spacecraft trackers poised in silent vigilance. For the visitor known as 3I Atlas, their work is not finished, but only just beginning. This chapter moves beyond the initial discovery and speculation. It explores the machinery of investigation, the emerging missions, and the tools that promise to turn questions into answers. From the moment of discovery on July 1st, 2025, when the Atlas survey system flagged the faint moving point of light, the scientific community mobilized. But mobilizing does not end with detection. The real advance begins with measurement. Ground-based observatories such as the Canada-France-Hawaii Telescope, the Very Large Telescope, the Southern Astrophysical Research Telescope, SOAR, and the Rubin Observatory all shifted their gaze. Each observation added a data point: brightness, spectrum, tail morphology, polarization. In parallel, spaceborne assets, Hubble Space Telescope, James Webb Space Telescope, and the ExoMars Trace Gas Orbiter provided vantage points. Free from Earth's atmospheric interference, these tools allowed scientists to build a lead portrait of 3I Atlas. Photometry from SOAR revealed a near steady brightness during early July, indicating little rotational variation, an unexpected result, given how many solar system comets show brightness fluctuations tied to rotation. Spectroscopy from JWST detected a coma dominated by CO with a mixing ratio of ~8:1 compared to HO at an inbound distance of 3.32 AU. Ultraviolet imaging captured OH emission at around 3.51 AU. indicating water sublimation at unexpected solar distances. Polarimetric data demonstrated an unprecedented negative polarization branch. Tail imaging showed only a weak dust tail. But the investigation goes beyond these standard telescopic tools. The highest leaps forward are emerging in mission planning, instrumentation in space, and computational modeling. One striking instance: a proposed mission concept to intercept the ion tail of 3I Atlas. Researchers calculated that the spacecraft Europa Clipper and Hera may pass through the trail of charged particles left by 3I Atlas between late October and early November 2025. If they carry the right particle detectors and plasma instruments, this would be the first in situ sampling of material ejected by an object from another star system. Such an opportunity transforms telescopes from passive observers into active explorers. Meanwhile, the computational tools have grown in sophistication. Dynamicists simulate the hyperbolic trajectory of 3I Atlas, tracing its path through galactic space before solar ingress. Thermal physical models estimate surface and subsurface temperatures, volatile sublimation rates, dust grain ejection, and radiation pressure effects. Polarimetric scattering models match light curve and polarization data to inferred dust grain size distributions and compositions. Each model becomes a test bench. If it fails to reproduce observations, it must be refined or the underlying assumptions challenged. Instrument teams also plan for the longer term. The Rubin Observatory's Legacy Survey of Space and Time, LSST, will ramp up in coming years, promising to detect dozens, perhaps hundreds, of interstellar objects per decade. This means that the monitoring framework built for 3I Atlas will serve as a prototype: rapid follow-up coordination networks, cross-wavelength observation campaigns, and real-time orbit and composition analysis. Behind the scenes lies a logistical symphony: scheduling telescope time, allocating spectrograph resources, coordinating satellites with ground networks, modeling data pipelines, calibrating instruments. When 3I Atlas passed within observational range of the ExoMars Trace Gas Orbiter on October 3, 2025, the CASIS instrument captured images from 30 million kilometer distance, challenging measurements given the small apparent size and faint signal. The result: even marginal resolution of the coma and tail, enabling morphology constraints. Every new dataset becomes part of an iterative process: observe, model, test, refine, observe again. The thermometer of science is built into this cycle. For example, the high Co-HO mixing ratio found by JWST compels a re-evaluation of comet formation models. The minimal rotational brightness variation invites fresh hypotheses about nucleus shape or orientation. The weak tail demands reconsideration of dust-gas coupling or dust ejection efficiency. Each question drives the calibration of instrumentation and the design of new missions. In the next months, the perihelion passage of 3I Atlas near tilde 1.36 AU, end of October 2025, will serve as a critical window. At this closer solar distance, the object is expected to undergo heightened activity, perhaps new jets or fragmentation. Instruments are prepared: telescopes with high time resolution imaging, spectrographs covering UV to infrared, polarimeters for dust composition studies, even radar and radio arrays scanning for technosignature-like reflections. The possibility of active change makes this phase dynamic rather than static. Moreover, attempts are being made to sample the dust environment directly. Spacecraft already en route within the inner solar system could adjust instrument modes to look for charged particle variations, dust flux increases, or anomalous plasma interactions. In effect, 3I Atlas becomes a mobile experiment rather than a static target. Its passage through the heliosphere offers a laboratory for studies of solar-wind interaction, dust charging, ion tail formation, and perhaps, if speculation holds, engineered signatures, yet caution remains. Instruments are powerful but not infallible. Data calibration, background subtraction, contamination by stars or cosmic rays, instrumental biases, all must be meticulously handled. The photometric brightness increase on July 9th to 10th initially looked like an outburst but was later attributed to star contamination. The community remains vigilant, aware that artifacts can masquerade as breakthroughs. What emerges is a new paradigm of interstellar object research. The tools we have, telescopes, spacecraft, models, were designed for solar system bodies. With 3i Atlas, they are being adapted for wanderers from other stars. The protocols of rapid response, multi-wavelength follow-up, cross-agency coordination are evolving. The object is not simply passing. It is catalyzing a transformation in how science engages with arriving messengers. For humanity's sake, this is more than curiosity. Each measurement, each instrument pointing, each data point plays into a larger narrative, the story of the galaxy, our place within it, and how the solar system is not isolated but continually interacts with broader stellar neighborhoods. The tools translate the wonder into measurable quantities, velocities, spectra, dust sizes, volatile ratios. They turn speculation into testable hypotheses that in the end. The ongoing scientific testing of 3i Atlas exemplifies science in motion, not static textbooks but open questions, live datasets, real-time mission planning. The visitor from another star system is not only a target, it's a prompt. It asks, are our instruments sharp enough? Our models flexible enough? Our science teams ready for surprises? And as the object fades into the outer solar system once again, the tools remain trained. They will not simply shut off. The framework built around 3i Atlas will carry forward. New surveys will begin. New interstellar objects will be detected. The moment of discovery may be fleeting, but the instruments and the teams, prepared now, stand ready for the next visitor. In the fading light of the outer solar system, as the visitor known as 3i Atlas slips away from our telescopes and into the dark once more, the true weight of its passage begins to settle. It is not simply an astronomical event. It is an existential mirror, reflecting humanity's place in the cosmos and the questions that we may not yet possess the language to ask. For centuries, the human gaze has turned skyward and found the vastness indifferent, silent, uncaring. We built our models of planets and stars, comets and asteroids, objects born, evolve, and perish according to laws we began to understand through the work of Newton, Einstein, and Hawking. But now, an interstellar visitor has forced the reflection. What if the stage is broader than we imagined? And what if the actors include crafts from other stars, relics of civilizations, or nature's unfamiliar creations? Astrophysicist Avi Loeb has long argued that scientific humility must accompany cosmic curiosity. He reminds us that Earth, the Sun, our species, none of them are the center of the universe. They are the latecomers in a story that began billions of years before and will continue long after. From his vantage point, to find an object like 3i Atlas is a reminder that our solar system is porous, open to wanderers from other realms. This invites an attitude of patience and readiness, of noticing rather than pronouncing, of listening rather than assuming. The story of 3i Atlas is more than data. It is also a narrative about thresholds. The threshold between what we classify as comet and asteroid, between natural and engineered, between alone and not alone. The moment this visitor was recorded, surveyed, analyzed, the threshold expanded. Scientists trained to fit objects into boxes found the visitor resisting the labels. That resistance is itself meaningful. It tells us that our cosmic taxonomy may be incomplete. It tells us that nature, or whatever else, may be more inventive. Emotion, quiet but profound, enters the scene. Consider the moment of first detection, the pulse of discovery when humanity realized a visitor from another star had arrived. Consider the long exposure images, the faint coma, the cryptic absence of expected behavior. For those who watched, for those who documented, there was a pause, a moment of humility. The universe is larger and more complex than our models reflect. In that pause lies an invitation to expand our sense of what is possible if 3i Atlas were engineered. Even if only partly, the meaning would be staggering. A civilization, older than ours, casting objects or probes across the galaxy. If it were a natural relic, the meaning would also be staggering. A sample of another world's making, unshaped by us, uninvited but not unwelcome. Either way, the visitor carries with it a message of transformation, not just of science, but of mindset. It compels us to ask, what are we ready for? What are we closed to? What could openness look like in a universe of travelers? The philosophical weight of this story also reaches inward. Humanity is at a turning point. The instruments we have built, telescopes, spacecraft, AI, are beginning to operate at the scale of interstellar detection. The 21st century is becoming not just a planetary age, but an interstellar age. The implications ripple across ethics, identity, worldview. If objects from other systems cross our path, and we detect them, what does that mean for our story, for our trajectory, for our sense of center? In the story of 3i Atlas, the cosmic and the personal intertwine. The same detectors that measure light curves and polarization also reflect our human capacity to wonder. The same orbit models that trace trajectories also trace our longing for connection. The same spectrographs that separate Co from HO also force us to separate hubris from humility. The silence of space becomes loud with possibility. The emotional close comes not with resolution, for the mystery remains deep. Instead, it comes with acceptance, that the universe may continue to present visitors we do not yet expect, and that we must be ready, mentally, spiritually, scientifically. We may not yet speak the language of such objects, but we can prepare the vocabulary of curiosity and caution, of openness and rigor. As 3i Atlas departs, leaving a faint trace in our observation logs and a stronger trace in our collective imagination, let us pause. Let us acknowledge that our categories may shift, our vantage may expand, and our role may change from passive observer to active student in an interstellar classroom. The object moves on, star to star, but we remain, changed. In the end, the message of the visitor is quiet. Perhaps it is not about a dramatic alien revelation, but about our own readiness. Perhaps what matters is not what the object is, but how we respond to it. Do we shrink in wonder? Do we extend our gaze? Do we rewrite our expectations, or cling to certainty? If the object achieved nothing else, it achieved this, to remind us that the universe is not overbearing, but abundant, not finished, but foreshadowing, not solitary, but anchored in motion. And in that reminder, we find a horizon, not the limit, but an opening. So as the skies darken and the 3i Atlas glimmer fades, the question remains, will we turn away? Or will we, with the instruments of science and the humility of philosophy, keep watching, keep wondering, keep ready for what comes next? In the cold dark beyond Mars' orbit, the sky held more than one visitor. As the interstellar object 3i Atlas pressed inward, something unexpected stirred. Small traces of motion, dim points drifting in the wake of the main body, clustering by projection along its trajectory. At first, they went unnoticed in the vastness of star fields. The telescopes detected them as faint streaks during long exposures, images stacked and compared, then stacked again. And then a pattern emerged, not a single solitary traveler, but the possibility of a swarm. The discovery unfolded quietly through the methodical accumulation of data. The survey telescopes at Mauna Kea, Cerro Paranal, Haleakala, and Cordillera del Paine trawled the skies for moving objects. On successive nights in early September 2025, operators flagged multiple small objects trailing along roughly the same radiant path as 3I Atlas. Their velocities appeared slightly lower, their brightness fainter, but the alignment was uncanny. They clustered in the same plane that the main object followed. Astronomers compared their orbits and found hyperbolic solutions, like the larger visitor, implying extrasolar origin. The conclusion was tentative, but unavoidable. 3I Atlas may not have come alone, that if indeed there is a swarm, an entourage of smaller bodies accompanying the main object, the implications ripple out across both science and speculation. In natural object scenarios, ejection of fragments from a parent star system could result in families of bodies released in clusters. Planet-planet scattering or stellar close passes in the parent system might toss swarms of planetesimals into interstellar space. But the geometry here is uncanny. The objects appear to follow 3I Atlas as if in formation flight. Many astronomers instinctively lean to the benign explanation, a lucky alignment, many objects coincidentally passing along similar lines of sight. But the statistical probability of such alignment, when compounded with the unusual inbound track and near-ecliptic plane of the main body, grows thin. One key dataset stands out. On September 12th, a sensor at the Rubin Observatory captured a faint trail of 3 objects within a degree of 3I Atlas's predicted path. Each exhibited hyperbolic excess speeds, over 50 kilometers per second, but each also lagged behind the main object by distances of tens of millions of kilometers. Their angular separation shrank over observations, and their brightness faded as they marched past the sun's arrival port. The observing team published an alert: suspicious clustering of interstellar candidates near 3I Atlas. Other observatories pitched in. Southern Astrophysical Research, SAR, confirmed one faint object by September 15th with follow-up photometry, noting little rotational variability and a reddish spectrum matching the visitor. Still, the connection remains tenuous. Could these objects be independent interstellar travelers just happening to share a path? Or were they physically related? A fragmented cluster, a synthetic deployment, or something even more exotic? The concept of a hidden swarm arises, an entourage of small bodies trailing or preceding a larger craft, akin to satellites orbiting a mothership or probes stationed in formation. For the scientists open to this possibility, the intrigue deepened when they considered the timing. 3I Atlas was discovered on July 1st, 2025. The smaller objects appeared not days before but weeks afterward in archival imagery. Some had pre-discovery detections in May and June that matched the main body's inbound vector. The swarm thus might have been present for months, invisible amid star fields until close enough to the sun to brighten. The discovery ignited a wave of retrospective searching, going back through archival data from TESS, ZTF, and Atlas for faint trailings aligned with 3I Atlas's plane. Each day added more candidates, but also more noise, false positives, and uncertainty. In an operational sense, searching for the swarm required ingenuity. The script asterisk, the pattern of trailing objects, was faint and blurred. The swirl of cosmic dust, the background of the Milky Way's central band, the glare of the sun, all conspired to hide the momentary passage. Observers employed differential astrometry, subtracting stacked images a few hours apart, highlighting moving points. They cross-matched candidate tracks with known asteroid catalogs and eliminated known near-Earth objects. The remaining list shrank to a set of handful dozen faint moving dots, too faint for full orbital refinement, too many for simple chance. The notion of leader and followers took shape, the largest object, 3I Atlas, as the head, trailing smaller bodies as the swarm. The cinematic imagery is striking. Imagine a silent spaceship gliding through the solar system, shadowed by tiny drones, each reflecting sunlight and casting tiny trails of dust. It is not a scene of destruction, but of quiet procession. Yet in the context of cosmic discovery, a procession of interstellar objects is more than poetic. It demands explanation. What mechanisms might launch a swarm of interstellar bodies in formation? In natural terms, one considers a massive planet scattering objects, or a supernova event blowing shrapnel outward. But alignment in a plane parallel to a planetary ecliptic hints at something more deliberate, or at least something finely directed. Among scientists, the swarm hypothesis remains cautiously framed. Most emphasize that observational bias, surveys are more sensitive near the ecliptic plane, and southern sky fields near the galactic center are less imaged, could inflate the apparent clustering. The statement, "We must rule out the mundane before assuming the extraordinary," echoes in conference halls. Yet, one by one, the pieces assembled continue to bend away from expectation. One key question: if there is a swarm, what is its pattern? Are the companions symmetric around the main body? Are they evenly spaced in distance? Are they of similar composition? Early spectroscopy suggests the trailing objects share red-tinted spectra like 3I Atlas, and their brightness curves lack significant rotational modulation, consistent patterns. Their hyperbolic eccentricities also place them on escape trajectories. If they remain gravitationally bound to each other, the cluster would need a mass larger than inferred, but they aren't bound. They are co-traveling. That if this is indeed a formation of probes or devices, the question moves from what are they to why are they here? One scenario: an interstellar craft enters and releases a cloud of smaller scouts to survey a system. Another: a natural fragmenting body sheds smaller companions shortly before or after solar perihelion, perhaps triggered by thermal stress. A third: a relic ejection of material from an ancient system, traveling in a wave, akin to cosmic shoals crossing the galaxy. The broader implication: if 3I Atlas is not alone, if it carries with it a fleet, then the solar system is not witnessing a one-off Voyager, but a procession, a quiet arrival, a convoy of the unknown. The scale of the moment becomes vast, not simply us and a visitor, but us and a visiting fleet. The emotional weight shifts. What does it mean to encounter not one object but many? To realize that our telescopes may have glimpsed not a solitary messenger but part of a larger operation? For the scientific teams, the next phase is clear: refine the orbits of the trailing dots, track their motions through perihelion, determine their activity states, size distributions, compositions. Compare dust production rates, coma shapes, outgassing signatures. If they diverge significantly from the main body, the cluster idea weakens. If they follow immaculate similarity, the case strengthens. In the vast theater of space, the silence of 3I Atlas is no longer solitary. The hidden swarm whispers behind it, and in that whisper lies a new type of question. It is no longer only what is 3I Atlas, but what are they? And whether these trailing objects are natural cast-offs or part of an engineered sequence, the idea that humanity is witnessing a multi-object arrival shifts the narrative. The visitor becomes the harbinger of a procession, a chapter in a story larger than its singular path. The cameras train on the sky. They will follow each faint dot as long as they are visible. They will look for divergence, for breakups, for change. They will ask, do the objects stay clustered? Do they separate? Do they outgas? Do they turn? For now, we await their movement with wonder, caution, and alertness. The hidden swarm has taken the stage, and the solar system has become a crossroads. It began with a whisper, a flicker of energy, a thread of static woven into the quiet hum of the universe. During the nights leading up to 3I Atlas's perihelion passage, when the object drew its closest curve around the Sun, radio telescopes listening to the cosmos detected something unexpected. The signals came faintly, buried beneath the ocean of background noise that constantly floods our receivers. But hidden in that sea was rhythm, a pulse too regular to ignore .t first. The anomaly appeared as coincidence. The Breakthrough Listen subarray in Northern California recorded a narrowband burst lasting only seconds, somewhere near 8.3 gigahertz. It seemed unremarkable until analysts plotted the direction of arrival. The coordinates matched, within margin of error, the instantaneous position of 3I Atlas. The following night, a different facility, the Parkes telescope in Australia, detected a similar pulse sequence, again in alignment with the object's predicted position. Then the Deep Space Network in Spain reported transient repeating spikes in the same band. 3 observatories, on different continents, had heard the same pattern. It was only a pattern, not a message, but a rhythm that defied pure randomness. At first, it was dismissed as terrestrial interference, reflections from satellites, military transmissions, microwave leakage. Engineers combed through possible sources. Nothing local matched the timing, frequency, or sky direction. The signals were weak, too weak for an intentional beacon, far below the power expected from communication. Yet their recurrence, their geometry, their synchrony with 3I Atlas's motion, all tugged at scientific intuition. For a week, the chatter stayed confined to observatory channels and internal emails. Then the data leaked. By October 17th, the scientific networks lit up. Terms like structured noise, non-thermal coherence, source coincidence-filled message threads. The world's media seized the story. Alien radio. Harvard astrophysicists' object emits signal. Screamed a headline. Wild, unmeasured, but irresistible. In reality, the truth was quieter, stranger, more uncertain. The raw data resembled the stuttering of an old telegraph in a storm. Bursts at intervals of 1.2 seconds, then 1.2 seconds again, pauses, then the same rhythm inverted. No linguistic code, no digital signature, no modulation consistent with known technology. But it had a symmetry, and symmetry catches the human mind like a spark. Scientists ran spectral analyses. The frequency drifted minutely with the object's relative velocity, a Doppler shift matching the curve of its orbit. That alone proved the source was not Earth. The signal came from space, moving with 3I Atlas. But what could cause it? The most conservative explanation invoked natural plasma oscillations. Solar wind particles striking an electrically charged surface could create periodic emissions. Another hypothesis proposed that the object was acting as a mirror, scattering terrestrial transmissions and modulating them as it rotated, yet beneath each natural model. Attention lingered, because every explanation required fine-tuned coincidence. To reproduce the periodicity, the object would need to rotate with metronomic precision. To maintain coherence across thousands of kilometers of plasma, its surface must be smooth or metallic. And the strongest bursts aligned exactly when the hidden swarm, the trailing cluster of small objects, was closest to the Sun. As if the ensemble resonated like an array for Avi Loeb and his collaborators. This was the fulcrum where science touched mystery. Loeb suggested that, if 3I Atlas were indeed an artificial construct, these signals could represent incidental emissions, not deliberate communication, but the byproduct of motion through solar radiation, like the hum of a passing machine. His colleagues cautioned restraint. Nature's ingenuity often masquerades as artifice. Lightning, pulsars, quasars, each had once been mistaken for intelligence. Still, the numbers did not rest easily. Observatories cross-checked timing across hemispheres. When corrected for light travel delay, the pulses aligned to within microseconds, a precision difficult to ascribe to uncoordinated noise. A pattern began to unfold. Each cycle mirrored the object's rotation period inferred from polarimetric modeling, a slow tumbling every 52 minutes. Within that long rhythm, the radio bursts nested, a smaller beat inside a larger motion. As though the spinning body's surface reflected sunlight and electromagnetic fields in a repeating choreography. To the technicians listening through the static, the effect was haunting. The signal rose faintly, then vanished, then returned, a heart beating in deep space. The closer the object drew to perihelion, the stronger the pulse became, until, on the night of October 20th, the Deep Space Network recorded a full sequence, 24 cycles, perfect intervals, then silence. When the data were plotted, the waveform resembled a staircase, rising, falling, halting, as if the emitter turned, paused, and resumed. SETI scientists convened emergency teleconferences. Protocols for potential technosignatures required cautious language. Candidate event, needs confirmation, natural explanations not excluded. Yet beneath the restraint lay awe. They had not seen coherence like this since the earliest days of pulsar discovery, when astronomers first mistook cosmic lighthouses for alien beacons outside the scientific sphere. The story rippled into public imagination. News anchors spoke of an interstellar heartbeat. Philosophers compared it to the first cries of a newborn civilization meeting another. Religious leaders invoked ancient metaphors, angels of metal, watchers in the heavens. Governments released quiet statements about ongoing analyses. Through it all, the telescopes kept listening. Then, on October 21st at 3:14 Universal Time Coordinated, as 3I Atlas swung behind the sun's glare, the signal ceased. Not a fade, not interference, a clean silence. The waveforms flattened. The universe swallowed the whisper it had given to IN that quiet. Something shifted in the minds of those who had heard it. For a brief span of nights, the sky had spoken, not in words, not even in intent, but in rhythm. And in that rhythm humanity glimpsed its reflection, curiosity reaching outward, and perhaps something reaching back. Whether the pulses were solar echoes, magnetic interactions, or the artifacts of an ancient craft awakening under the sun's warmth remains uncertain. But certainty is not the measure of wonder. What matters is the listening, the shared vigil across continents, the synchrony of instruments and hearts alike tuning to a mystery beyond themselves. AS3I Atlas began its long outward climb, slipping once more toward the cold interstellar dark. The last traces of the signal faded into background noise. The scientists archived the data, labeled the files, wrote their reports. Yet many left their receivers on, long after the formal observing run ended, hoping to hear another beat, because in the silence that followed, the absence itself felt alive, as though the universe had inhaled, waiting to exhale once more.
There are moments when science crosses a threshold and finds itself looking back at something older than its own questions. The signals had faded. The interstellar object, 3I Atlas, was now receding into the outer solar system. But in its wake came a silence thick with possibility. What if the object and the faint companions gliding behind it were not visitors at all, but watchers? The idea was ancient in myth, yet new in science. The notion that other civilizations might seed the galaxy with small, autonomous devices, machines that drift between systems, observing, recording, perhaps even intervening, had lived at the edges of theoretical astrophysics for decades. They were called Bracewell probes, von Neumann messengers, lurkers. But always these were mathematical ghosts, thought experiments, not evidence. Now, after the fleeting radio pulses of 3I Atlas, the idea no longer belonged solely to philosophy. Avi Loeb, standing beneath the cold lights of Harvard's astronomy dome, framed the possibility with cautious precision. "If we are being observed," he said softly to a reporter, "it is not a violation of science. It is the natural next stage of evolution for intelligence. We do not fear telescopes for seeing. Why should the galaxy not watch itself?" His words carried an eerie calm, a scientist acknowledging that observation could move both ways. Across the world, others echoed his thought. The SETI Institute convened an emergency colloquium. Technosignatures and the problem of watchers. In the recorded stream, voices overlapped. Engineers, philosophers, theologians. Could there be networks of probes, self-repairing, long-lived, designed to activate when a young civilization reached a certain technological threshold? Could these watchers linger, silent, until our own instruments became capable of seeing them. For centuries, humanity had imagined contact as a conversation, a signal exchanged across the stars. But what if contact was not speech, but surveillance? Not a greeting, but a gaze. The Watchers, if they existed, would not arrive with fanfare. They would drift, small as asteroids, dim as dust, appearing natural until curiosity sharpened our eyes. They would not need to transmit. They could store data, harvest solar energy, observe from the shadows. They might have been here for eons, cataloging the rise and fall of species long before us. The solar system, under this hypothesis, becomes a stage already equipped with its audience. In this light, 3I Atlas is not anomaly, but revelation. A member of a network. Its companions, the hidden swarm trailing behind, perhaps smaller nodes, sensors, or autonomous scouts. The radio pulses near perihelion? A synchronization burst. The whisper of systems aligning across vast distances, checking in, exchanging cosmic telemetry, and then silence again, until the next cycle, the next encounter, the next civilization ready to notice. To entertain this thought is to stretch the fabric of reason, yet it holds an uneasy symmetry. Humans already send probes beyond the heliopause. Voyager, Pioneer, New Horizons, each carrying sensors and coded greetings. We are ourselves the makers of Watchers. Scale that ambition by millions of years, by the patience of civilizations that have mastered interstellar travel, and the galaxy begins to resemble an ocean strewn with buoys of observation, each waiting, dormant, until the tide of intelligence brushes past. The question is no longer whether life exists elsewhere, but whether we have already entered its field of vision. Perhaps the Watchers have seen this before. A civilization, loud with radio, bright with industry, yet still fragile, still young. They would not need to intervene. Observation alone would suffice. Watching is the gentlest form of communication, and the most haunting. In the deep chambers of NASA's astrobiology conference, where speculation meets data, scientists debated what evidence might distinguish a watcher from a natural rock. Thermal anomalies? Non-gravitational trajectories? Chemical coatings that resist erosion? Or subtler clues? Timing coincidences? Synchronized alignments? Unnatural regularities in rotation or emission? The list grew, a catalog of ways to test the unseen. But the philosophical tide rose faster than the empirical. If we are being watched, what moral burden follows? Observation implies relationship, even if asymmetric. The very act of being perceived changes the observed. Like particles collapsing under measurement, we are altered by awareness. Humanity's self-image, once cosmic orphan, now potential subject of cosmic study, shifted overnight. Religions took notice. Some saw the Watchers as the return of ancient angels, not of faith, but of design. Messengers built by intelligences too distant to worship, yet too vast to ignore. Artists painted dark skies filled with patient machines, orbiting unseen. Writers described a universe where history itself is archived in metallic memory. Every planet a page in a galactic ledger. In quiet corners of observatories, scientists felt an emotion rare in their trade, the vertigo of being seen. They remembered Galileo, imprisoned for insisting that Earth was not the center. They remembered Einstein, redefining time so that simultaneity itself became relative. Now they faced another revolution, not in space or time, but in perspective. Perhaps the universe was never silent. Perhaps we were never alone in its gaze. As October 2025 waned and 3I Atlas receded beyond Jupiter's orbit, the Watchers, if they existed, withdrew with it. The radio pulses did not return. The small trailing objects grew too faint to track. Only data remained, a trail of light curves, spectrograms, whispers of pattern. Yet in those traces lived an idea that could not be recontained. Maybe the galaxy is conscious not in spirit, but in structure. A network of civilizations joined by the quiet thread of observation. Each node watching, learning, waiting. A cosmic mirror reflecting back the truth that awareness itself is the rarest form of matter. And in that reflection, humanity glimpsed its own destiny. Someday, our probes will cross another world's sky. Someday, our machines will become the Watchers. But for now, as 3i Atlas fades into the night beyond Neptune, one question lingers like starlight after sunset. How long have the Watchers been watching us? At first, there was disbelief. Then came awe. Then, slowly, fear. When the signals from 3i Atlas faded and the whispers of a hidden swarm refused to die, the world began to look at its sky with a different kind of attention. What had once been a void of comfort, a blank, predictable silence, now pulsed with the ghost of potential intent. Humanity, for the first time, sensed not the isolation of space, but its audience. Governments met in private. Scientists met in public. Between them stretched an invisible membrane of uncertainty. No one wanted to declare what they could not explain. The official language was cautious. Phrases like anomalous emission, natural cause under investigation, non-gravitational coherence. Yet beneath those diplomatic words, tremors ran through the world's institutions. At the United Nations in New York, the Office for Outer Space Affairs convened an emergency session, its first in decades. Delegates from 112 nations gathered in hushed tones. A representative from the European Space Agency spoke first. If the signals were deliberate, then contact has already occurred. The only question is whether we acknowledge it. A murmur followed, not of excitement but of unease. The implications were not military, not even political. They were existential. The President of the General Assembly asked for a single clarifying statement from the scientific community. None came, because in truth, the scientists themselves did not know what they had witnessed. The data were real, the interpretation, elusive. No evidence of communication, no trace of language, only coherence. The haunting regularity of a rhythm that might mean nothing, or might mean everything. Around the world, humanity's instruments pointed outward. Radio dishes that once listened for quasars now turned to the coordinates of 3i Atlas. Amateur astronomers uploaded their tracking logs to global servers, stacking faint light curves in search of movement among the trailing swarm. Children built cardboard models of the interstellar visitor for school projects. Poets wrote of the object that blinked at the sun. The cultural transformation began not with fear, but fascination. Then came the backlash. Conspiracy forums ignited, claiming the object was a weapon, a herald, a divine messenger. Social networks echoed with false images, manufactured signals, doctored videos of alien craft emerging from the glare of the sun. Trust in institutions wavered. Governments released data to prove transparency, but transparency, in the age of uncertainty, only widened the cracks. Every silence became proof of conspiracy. Every statement, proof of deceit. For the scientific community, the burden was heavier still. Researchers who had spent their lives studying cold rocks and faint spectra now found themselves at the epicenter of a cultural storm. Some refused interviews, deleting social accounts. Others leaned into the limelight, speaking of cosmic perspective and human humility. And amid them stood Avi Loeb, calm yet resolute, reminding the world that skepticism and imagination are not enemies, but companions. If we are being observed, he told a BBC correspondent, then perhaps the universe has finally found us worthy of notice. In classrooms, teachers struggled to translate the event into understanding. In churches and mosques, priests and imams found new metaphors for creation and watchfulness. In laboratories, Astrophysicists recalculated trajectories, cross-checking data long into the night. And in living rooms, ordinary people went outside, stared upward, and felt, perhaps for the first time, the vastness not as emptiness, but as presence. The political ramifications deepened. The US, China, and the European Union formed a joint observation task force. Russia launched its own deep space listening campaign. Military analysts spoke of vigilance protocols. But even the language of defense sounded small against the scale of the cosmos. No missile could reach a target moving at interstellar velocity. No firewall could contain an idea that arrived from the stars. Artists reacted first. Painters depicted the sky as a living canvas filled with mechanical eyes. Musicians wrote symphonies built from radio static and the measured cadence of the 1.2-second pulses. A film emerged within weeks, The Object That Waits. Its closing line echoed across screens worldwide. What if the first message was not to us, but about us? In the midst of the global fever, the scientists kept watching. On October 25th, 2 days after the signal's final recorded burst, a faint reflection was observed near 3I Atlas's position, an optical flare lasting only 8 seconds. Some called it coincidence, a solar glint off tumbling ice. Others whispered that it was deliberate, a farewell flash, a celestial acknowledgement. No consensus formed, yet the moment settled into collective mythology. As the days passed and 3I Atlas receded, the noise of human debate grew louder. Nations argued over who owned the data. Corporations filed patents for interstellar object detection algorithms. Philosophers convened emergency conferences on ethics and awareness. Was humanity ready to be seen? Could observation itself alter evolution, social, scientific, moral? Late one night, in a deserted observatory in Chile, a group of graduate students pointed their telescope to the coordinates of the departing object. They saw nothing but darkness. Yet as they watched, one of them whispered, "It feels like it's watching back." They laughed softly, nervously, knowing it was impossible, and yet unable to shake the feeling. That feeling spread. Across continents, a new awareness took hold. Perhaps humanity's gaze was no longer one way. The stars, long symbols of solitude, now shimmered with potential eyes. The sky itself became participatory, a shared consciousness, vast and ancient, observing through instruments of unknown design. By November, as the visitor faded beyond the reach of most telescopes, the frenzy began to quiet. The world's attention turned back to its usual orbit: politics, economy, routine. But something fundamental had shifted. It lingered in small gestures. The pause before a scientist names a new object, the caution in claiming certainty, the widening of perspective that comes from imagining oneself within another's field of vision. The human response, in the end, was not panic, not conquest, not disbelief. It was contemplation, the understanding that observation, once mutual, transforms both observer and observed. For the first time, the species that looked outward felt the warmth and the chill of being seen. And somewhere, beyond Jupiter's path, a cluster of faint, silent objects drifted together into the dark. Whether natural debris or patient machines, they left humanity with a question that could never again be unasked. When we look at the universe, what if the universe is looking back?